Okay, welcome back to the next lecture on energy conservation and waste heat recovery. And today what we will do is, as you know, over the last two lectures we were discussing about heat pumps for waste heat recovery. So today we will just look at one more example and then conclude this lecture with a summary of what we discussed. So the last one that we are going to talk about is again an combination is an example of air, and this is used for drying of timber. Okay, think about it. For drying, what do we need? For drying of timber, or let us say even in a paper mill for drying of paper yarns, or even textile industry for drying of textiles, we need, if we are talking about air drying, we need hot air, and that air also has to be dry. Okay, the air cannot have moisture content. So this is going to be a challenge. How do we first dehumidify the air and then heat it up and so on. So one of the way, exactly in the order that I described, how do I dehumidify the air first and then heat it up? Heat pump again is a wonderful technique. Okay, using the vapor compression cycle, heat pump can be used. How? Let us look at this. Let us consider a stack of timber like this. Okay, this is pictorially represented in this manner, in a very simple manner like this, and let us say this is my stack of dry timber which needs to be dried. All right. So what I will do over here is, as I said, I am going to use a vapor compression cycle once more. So let me draw that vapor compression cycle again. Here I have a compressor, let me say here I have my condenser, then my expansion valve, and then my evaporator, and then the outlet of the evaporator goes to compressor. So this is my vapor compression cycle, as we know. What do I need? I have air, and I need hot dry air to come and dry this timber. So this is a stack of moist timber. Okay. So I need to dry this. How will I do it is the next question. So what I will do is, I have room air. I will first draw the loop and then we will talk about it. So this air actually passes through the evaporator, okay, and after the evaporator it is directed towards the condenser. So remember, this is a sequential, is the same fluid, first it goes to the evaporator, then it goes to the condenser. Probably we will have a fan over here to drive it back here. So let me first draw some boundaries. Okay. So the compressor and probably even the expansion valve can be outside. So what needs to be inside this timber drying unit is this. Okay. So what is happening? So the first thing is, let me write down each of them one by one. The humid air from timber stack passes across the heat pump evaporator. Now as it does, what happens? The temperature drops down below the dew point, and therefore, it loses the moisture. Okay. So, I would say that as a result of cooling, so cooling of this moist air, water vapor in the air condenses. Okay. Why? Because the temperature falls below the dew point and is drained off. So, below the evaporator we will have a collector where the water drains off. Okay. All right. So, I would write here as, I would name this as moisture capture. Okay. So, then I would say is the dry cooled air is next upgraded. Okay. So, it is next upgraded how? By sending it through the evaporator, by sending it through the condenser. So, as it goes to the condenser, it picks up heat from the refrigerant and its temperature goes up. Okay. By flowing through the condenser. So, here what it does is it gives up heat and therefore, the temperature goes up, it absorbs heat because the refrigerant gives up heat, and so the temperature goes up. So, results in dry hot air. Okay. So, let us quickly write this down. This one is what? It is dry hot air. What is this? This is also dry, but this is dry cold air. This one is moist hot air. So, the dry hot air, as it coming out of the condenser, when it passes through the stack, it dries the moisture, or it dries the timber, and therefore picks up moisture. So, what comes out is a moist hot air. I would say hot, or probably it also loses some heat to the moist timber. So, it will be warm air. Let me correct this and say this is warm air. Okay. It is moist warm air which flows to the evaporator where the temperature cools down to below the dew point. So, the moisture separates out and is captured below, and what comes out of the evaporator is dried and cooled air. So, I have got the dry part, but then I also need to heat it up, where it is which is done by passing it over the condenser, and the output there is dry hot air, which I can use for the drying of my timber. So, the same principle can also be used for a paper yarn manufacturer. They also use for drying their yarn, they also use heat pump. Okay. So, this configuration in different form, but it is the same principle, that if you have a drying application where you want to use a gas or air, you first pass it through the evaporator. When you pass it through the evaporator, you can separate the moisture out, because the temperature, you have to design the evaporator such that the temperature of that gas, in this case air, goes below the dew point under those conditions. Okay. So, therefore, the moisture condenses and is separated out, and what comes out of the evaporator of the heat pump is dry air, But remember, just dry is not enough, we have to heat it up as well. So therefore, the same dry air at a lower temperature coming out of the evaporator is upgraded by passing it over the condenser. So as it passes over the condenser, it picks up heat from the refrigerant, it heats up itself, and what comes out therefore is hot and dry, which is what we need for our drying application. Clear? So that is the overall principle of operation of heat pumps for drying applications. So what I showed here is, again I repeat, that it is for a stack of timbers, but you can think of a same application using the same principle, maybe in a different form, for drying of paper, drying of fabrics, and so on. Clear? All right. So that kind of brings us towards the end of our discussion on heat pumps. Okay. So let us do a quick recap and see what all we studied. Okay. So heat pump summary. If we want to tabulate, so we started by saying that how does a heat pump work. Okay. So I would say functioning, or principle of operation. Clear? And we said that the functioning or the principle of operation is basically a vapor compression refrigeration cycle by which the fluid at a lower temperature, the waste heat at a lower temperature can be upgraded to a higher temperature. Of course, it does not come for free, because in a heat pump using a vapor compression cycle you need compressor which needs electrical power, right. So you have to spend energy, and only then can you upgrade the heat from a lower upgrade thermal energy from a lower temperature to higher temperature. Clear? So we know that, and so we have flow of heat from a lower temperature to a higher temperature only when we have external work done on a system, right, and this is what is done. So that is the principle of operation of a heat pump. Next, what we did was we went straight away into applications. So we saw that heat pumps is ideal when you need simultaneously, so simultaneous requirement of cooling and heating. How can we and what are the different ways that we can do it, or what are the different scenarios under which you need both heating and cooling? We can think of a factory where you need two processes, one requires heating, another requires cooling, or you can have a single process stream wherein at one location you need it to be cooled, and then later you need it to be heated, right, and we saw examples of that. Okay. So then what we did was we looked at few specific examples, those were generic scenarios. One of them was year-round air conditioning, right. So this was a reversible heat pump that we talked about. Remember, we talked about a reversible heat pump where using a four-way switch we were able to switch the evaporator and condenser, or switch the evaporator and condenser, or rather use the heat exchanger that we have inside the room as an evaporator in summer so that it leads to cooling, and as a condenser in winter so that it leads to heating. Okay. So we looked at this application, and it was a wonderful example of heat pump. Again, remember that in summer while we had cooling by passing the hot outside air over the evaporator, we also had additional or air at a still higher temperature at the condenser end. Okay. So that can be used for various purposes. So heated air, that is thermal energy at high quality, has lots of applications. You can use it for washing clothes if it is a domestic application, you can use it for some process if it is an industrial application where you need heating. Clear? Similarly, during winter while we were getting heated air inside the room or inside the small industrial unit, we are also getting chilled air at the evaporator end, and this chilled air can also find applications. Okay. Another example that we talked about was that of injection molding. Where what did we use? Where the output, where we could think of using water, for example, at room temperature, whatever we have, using a heat pump, the same water goes over the evaporator and gives rise to chilled water. The chilled water can be circulated around the injection mold, so that the plastics get solidified and we get the product in the form and shape that we want. Okay. At the condenser end, again the room temperature water can be used as the fluid, at the heat exchange fluid, so that what comes out is heated water. Okay. That heated water can be used for factory space heating. Okay. Or we can also use air as the fluid in the condenser, where you get directly heated air, which we can directly provide to the factory floor. In case of water, heated water, we will pass it through some of these room heaters that use recirculating hot water or hot fluid. Clear? So, injection molding was one industrial example that we looked at. What else? We looked at a swimming pool example. Swimming pool heating. Again here, this was during winter. We took an example where the water in winter is probably at around, if let alone, would be around 15 degrees centigrade and all, which is not ideal for swimming. It is not an ergonomic temperature. So, what do we have to do? We have to heat it up. If we are talking about an industrial, of an indoor swimming pool or a swimming pool inside a hotel or even outside, so we have to heat up the water. So, how do we want to do that? Again, use a heat pump, use a refrigeration cycle, and use this use this water at 15 degrees centigrade that we have as the working fluid in the condenser, not the working fluid, sorry, as the heat exchange fluid in the condenser. The working fluid in the condenser is the refrigerant, right. So, therefore, what comes out will be heated water, which is pumped back to the swimming pool, and this is how this loop is continuous. And so, the swimming pool water is recirculated through the condenser or pumped through the condenser, and this is how we get hot water for swimming. And at the evaporator end, again the same water at ambient temperature can be used as the heat exchange fluid, and what will come out is chilled water, which again can be used for various applications. We can think of ways to use chilled water. Okay. All right. So, that was another example. One wonderful application which has been there for many years now is the Westinghouse Template, right. In Template, what we use, it is water again, and we use a two-stage compression. It is a two-stage compression, therefore, two compressors and two expansion valves. We also drew the thermodynamic pH diagram to show the different points of, because this is a two-stage cycle. Now, why do we need a two-stage cycle? Because remember, the water which is available to us, the waste water, is at 32 degrees centigrade, and what we desire to have is a temperature around above 80 degrees centigrade. So, the temperature gradient is very high, right. So, temperature gradient of the water itself, the upgradation of water itself is very high, and therefore, the temperature gradient of the refrigerant at the evaporator and condenser is even higher. It is around 25 degrees at the evaporator, and it is 90 degrees or above at the condenser. So, because of this large delta T, we do not want to use a single compressor to go through this large pressure ratio, rather therefore, we use it in two stages. There is a low pressure compressor, and then there is a high pressure compressor. So, two stage compression. So, cycle gets a little complicated, but that does not matter. Finally, I mean, from the refrigeration cycle point of view, yes, it makes it complicated, but for our application, what we are looking at, finally we are going to use the evaporator for cooling and the condenser for heating, right. So, as before, we use water from or wastewater from a process and heat it up again by flowing it through the condenser, and we get water at 80 degrees and above. Okay. So, this is how we upgrade water available to us at 32 degrees centigrade to 80 degrees centigrade or higher. Okay. And the last application that we talked about was an example of drying of timber. This can be, we saw it as timber, but also applicable for paper, textiles, etc. So, drying of timber, what do we use? We would like to use air drying in this case. So, what are the characteristics of what are the qualities of air that we need? We need the air to be hot and we need the air to be dry. Okay. We need the air to be hot so that the moisture trapped in the timber can evaporate and be carried out by the can evaporate and be carried out, and we need the air to be dry because the air should be able to absorb the moisture that is inside the timber. Okay. So, therefore, what we do is the air that is available to us or that comes out of the timber is going to be moist air. So, we need to first remove the moisture. The way we do it is again using a heat pump, and we pass that moist air through the evaporator. So, as it flows to the evaporator, its temperature goes down, and so therefore, it releases the moisture and the moisture is captured, and the dry air is the product of the that is coming out of the evaporator. The dry air then goes to the condenser where it picks up heat, becomes heated, and therefore, the product coming out of the condenser is hot and dry air, which is now used for drying of timber. Okay. This is what we discussed in this lecture itself. So, I am not going through a very detailed recap, because this is something that we studied very recently. Okay. So, this kind of sums up the heat pump summary. Clear? One passing note, thermoelectric generators that is part of a direct conversion device also works on the refrigeration or a similar principle. It does not have a condenser, evaporator, etc., but there also you have a hot junction, a cold junction, and external work done on it due to electric current flowing through the thermoelectric modules. Okay. So, you can think of it also as a heat pump. All right. So, if you say, let us see, you have a cold fluid and you have it at the cold end of the thermoelectric generator, and you have at the hotter end you have you can upgrade it and heat it up. Okay. So, it is the other way, because in this case it is no longer thermoelectric generator, but here you have to apply additional energy. You are not generating electricity, but you are applying additional energy but through an electric current that flows through the thermoelectric, in this case the thermoelectric cooler. So, therefore, what happens is you give rise to a temperature gradient and use the hot end for upgrading the quality of your waste heat. Okay. So, this is just a passing remark. Thermoelectric generator is what is part of this course, and there the focus is on electricity generation because of a temperature gradient across the thermoelectric module. But the other way the thermoelectric module can be used is also as a cooler or refrigerator, where actually the electric current is the input as an external energy, the external energy that is the external work that is done on the system, similar to compressor work here, and as a result you have a cold end, you give rise to a temperature gradient, and the temperature gradient can be used for upgradation of the waste heat that is available at a lower temperature. Okay. All right. So, with that concluding remark, we will wrap up our section and discussion on heat pumps. Okay. I hope I think heat pump, from your basic understanding of applied thermodynamics, you would have learnt, but in this course or in this few lectures, what we tried to do was look at it from the context of waste heat recovery, and the focus of this module was primarily on applications, right, where the heat pump principle, which is known to us, we saw a few applications where it is used in various industries for residential heating and cooling, and for swimming pool heating, and also for other industrial applications. Okay. All right. So, we will conclude our discussions on heat pumps, and in the next class we will take up a new topic, which is incinerating plants or incineration plants. Okay. So, till then, thank you very much and see you in the next lecture.